In exercise 13.2, they're giving us the name or the names for a couple of alcohols, and they're asking us to draw the structures of them. Now, when you do this, the first thing you want to do is to draw the backbone. And to decipher what this is in this long, complicated looking name, I would actually recommend that you kind of look at this from the right to the left. So at the right of this molecule, the suffix is the ending. That tells us the functional group we have. Then we see that the OL is there. So that means we have an alcohol somewhere, that OH somewhere. Moving to the left, we have the infix. That tells us about the bonding. So here we know we have all single bonds in the backbone. The prefix in front of that, hex, tells us the number of carbons. So this is 6 carbons in the backbone. And in front of that, we see the prefix cyclo. That means that these are going to be in a ring. Now this whole thing all together, that is the, this whole thing all together is the backbone name. Okay, so let's try to draw that backbone all by itself, then we'll worry about the branches. So if we want a 6-carbon ring, what does that look like? It looks a little bit like a hexagon. So the cyclohex would tell you to draw something like this, 6-membered ring. And then AN means we have all single bonds, and then the suffix OL means we have an OH somewhere. And we don't know where the OH is. I'm just going to draw it here at the top, the OH. Okay, so there's cyclohexanol. Now we're drawing this, so we get to number it however we want. We just have to put in the carbon number 1 where the OH is attached. I'm going to number it clockwise. You could just as well number it counterclockwise. You'll end up getting the same molecule, even if it looks a little bit different. Remember, these are 3-dimensional, and so you can flip them like pancakes or turn them like dials. And so even 2 molecules that may look different at first could be the same 3-dimensional molecule. But I'm going to draw this, number this clockwise. Okay, now we do have 2 branches. They're both coming off of carbon number 3. So, here's one of our branches coming off of carbon 3 and a second branch coming off of carbon number 3. And what types of branches are these? They're the same type of branch, hence we have that prefix di, and the rest of this is telling us that the branch itself is a bromine. Remember, with the halogens, that's everything in group 7A. As we talked about in the first video on naming in this chapter, the halogens are named by taking the first syllable and just adding an O at the end. So if you look at on the right side of the periodic table, group 7A, you'll see fluorine, chlorine, bromine, and iodine. Where you take the first syllable of all those and then just add an O, that's the names of these things when there are branches. And so you can see that when bromine is a branch, it's called bromo. That's exactly what we have here in this exercise here. So we have this bromo here. So we're going to have 2 bromine branches coming off of carbon number 3. Bromine and bromine. Now that would be the whole thing, except we have this R in front, and that means that we have a right-handed chiral center. But notice that because there's only one chiral center there, they don't give us a number to say where the chiral center is. So we have to figure it out. The chiral center is where we have 4 different things bonded to these carbons. Now each of these carbons can only have 4 bonds. So if a carbon is bonded to the same thing twice, if it's bonded to the same type of branch twice, then automatically we know it can't be the chiral center. Let me draw in the hydrogens here. I think that'll help us to identify where our chiral center is. So each of these carbons has 2 implied hydrogens. And if that's not familiar to you, let me know, and I can direct you to a video made for Organic Chemistry 1 that helps you to get used to seeing these skeletal structures. Okay, so one at a time, notice that this carbon is bonded to hydrogen twice. So it can't be bonded to 4 different things. That's not our chiral center. Oops. Okay, this carbon is bonded to bromine twice. It's bonded to two branches that are the same, so it can't be bonded to four different things, so that's not the chiral center. Likewise, each of the rest of these carbons is bonded to hydrogen twice. So it's bonded to the same type of branch twice. And so none of them could be chiral centers. Which means that the chiral center has to be where the OH is. Now I had a regular line there, but I need to replace that either with a solid wedge or with a dashed wedge. Remember that regular lines mean the bond is in the plane of the page. A solid wedge means it's coming out at you. A dashed wedge means it's going away from you. And we need to give the arrangement of this so that we have an R, a right-handed chiral center there. Okay, so how do we know to write a solid wedge or a dashed wedge? Well, we don't. So let's write both of them and see which one gives us an R chiral center. So let's try it with a solid wedge. Let's try it with a dashed wedge. Okay, I'm actually going to do this one at the bottom first. Let's see here. And so we're going to use the CIP rules, the same ones that we've used in previous videos. And so the first thing we want to do is to assign priorities. We know that the oxygen has the highest atomic number of 8, so it gets the highest priority of 1. Next, we have 2 carbons on each side, and the other thing that we have is a hydrogen. Now the hydrogen is implied, and the other thing you would want to remember is that this hydrogen has to be coming out at us. It's really important that you can recognize that. The way you know that, and we've discussed this in previous videos for this chapter, this carbon is tetrahedral, and it has 4 bonds and 0 lone pairs. You have 2 bonds in the plane and 1 going away. That means the other one has to be coming out. For these tetrahedral atoms, you will always have 2 bonds in the plane, 1 coming out and 1 going away. So if what's drawn is going away, then what isn't drawn must be coming out here. Okay, well, hydrogen has the lowest atomic number on the periodic table, so it has the lowest priority. Now the 2 carbons tie, and if you draw out the tables for these, and I'm just going to do this very fast because we've done this in previous videos. So if you draw out the tables for these, the one on the right is bonded to a carbon and 2 hydrogens, and the one on the left is bonded to a carbon and 2 hydrogens. And so when you compare them, they all tie. So you go to consider these 2. You draw a table for them. The one on the right is bonded to 2 bromines and a carbon. The one on the left is bonded to a carbon and 2 hydrogens. So the bromines have a higher atomic number, and so they get the higher priority. This was 2, and this is 3. So I did that a little fast, but if you don't feel comfortable with doing that, let me know, and I can direct you to videos from Organic Chemistry 1, where you would have learned and practiced that at more length. Here, we have bigger fish to fry. Okay, so we have 1 carbon, we've assigned the priorities. In the second case, we want to make sure that 4 is pointing away. Now 4 is not pointing away, it's pointing out at us here. So what we're going to do is we're going to make a mental note. 4 is pointing out at us. We're going to go, as usual, from carbon 1 to carbon 2 to carbon 3, ignoring 4. We'll see what it looks like it is. Here we're going clockwise, so it looks like it would be R, because as you go from the top to the bottom of an R, you go clockwise. But because 4 was coming toward us, we switch it. So it's actually S. And that's what you do if 4 is ever coming out at you. If 4 is coming out at you, go from 1 to 2 to 3, see what you would get, and switch it. So that is an S chiral center. What we wanted was an R chiral center. And so this is not going to be the drawing for this molecule. Compare that with this other arrangement. Let's draw this in. Notice that the hydrogen here is going to be going away because we have, at this chiral center here, we had 2 bonds in the plane, 1 coming out at us, the other one has to be going away. And in this case, just like before, the priorities are the same. The oxygen is 1, the hydrogen is 4, the carbon on the right is 2, the carbon on the left is 3. If you go from, notice that 4 is pointing away in this molecule. So if you go from 1 to 2 to 3, you go clockwise, you think it's an R, and that's what you want. So this molecule on the top is the correct drawing for, and I'll erase the hydrogen there because it's implied, that's the correct drawing for this molecule. That's the correct drawing for R,3,3-dibromocyclohexanol. Okay, so maybe doing that chiral center was a little tricky, but you look to see which carbon atom is bonded to 4 different things, which one is not bonded to the same type of branch twice. Draw that carbon once with the solid wedge, once with the dashed wedge, and see which structure gives you the correct chiral center. And that's the answer. Okay, let's try that again. Let's try that with B. So we'll try to lock in our skills here. So you'll see at the end of this we have a suffix, all. That means that we have an OH on the molecule. To the left of that we have an infix AN. That means that we have all single bonds. In front of that we have a prefix pent, and that means we have 5 carbons. And then we have a number. The number here is 3. The number is really telling us where the alcohol is. So this 3 goes with the OH. Okay, 5 carbons. 1, 2, 3, 4, 5. Now, we're drawing the molecule, so we get to number it however we want. I'm going to number it going left to right. So 1, 2, 3, 4, 5. If you number it the other way, it may look a little different at first, but remember these are 3-dimensional molecules, and if you rotate it in space, you'd really end up with the same molecule. So I'm going to number it right to left. You could or left to right. You could number it right to left and still get the same answer, a correct answer. Okay, so on carbon number 3, we have our OH. So I'll draw that in. We have 5 carbons, which took care of, and all single bonds, so we don't have to draw any double or triple bonds here. So far that's 3-pentanol. Okay, we have 2 branches, one branch coming off of carbon number 2, right? And one branch coming off of carbon number 3. So another branch here. What are those branches? Well, they're the same type of branch. They're the same type of branch. We can see that with this prefix here. And the type of branch that they are is a methyl branch. Now remember, meth is the prefix for just 1 carbon. And so we're only going to have 1 carbon in these branches. Okay, now that would be 2,3-dimethyl 3-pentanol. But we're not completely out of the woods because we still have this S here. So we need to make sure that wherever the chiral center is in this molecule, and they don't tell us because there's only 1, wherever it is, it needs to be an S. So which carbon here is bonded to 4 different groups? And it might help a little bit to draw, if I draw the hydrogens in to see. So here we have 3 hydrogens on that carbon, 2 hydrogens on this carbon, 3 hydrogens on this carbon, 1 hydrogen on this one, 3 here, and 3 here. Okay, with the hydrogens there, it always looks a little messier. Let's just look at this one at a time. If a carbon can only form 4 bonds, and so if it's bonded to the same type of thing more than once, then it can't be bonded to 4 different things. and it can't be chiral. Because this carbon on the right is bonded to the same type of thing 3 times, it can't be chiral. It's only because the next carbon is bonded to the same type of thing twice, it can't be chiral. Let's jump over a little bit. Because this carbon up here is bonded to a hydrogen 3 times, it can't be chiral. Because this carbon down here is bonded to a hydrogen 3 times, it can't be bonded to 4 different things, so it can't be chiral. Same thing for this carbon here. If it's bonded to hydrogen 3 times, that means that it can't be bonded to 4 different things. Finally, this carbon here is only bonded to 1 hydrogen, but notice it's bonded to 2 methyl groups. It's bonded to the same thing more than once, 2 methyl groups. And so that is also not chiral. So the only carbon that could possibly be chiral is that one there. And you'll notice that that is bonded to 4 different groups. It's bonded to an ethyl group, it's bonded to a methyl group, it's bonded to an OH, and it's bonded to an isopropyl group. And if that name isopropyl group doesn't sound familiar, I encourage you to watch the video. It's a name that'll come back. I encourage you to watch the video on branches that have branches, naming branches that have branches in the Organic Chemistry 1 review playlist. So this carbon here is bonded to 4 different groups, and so it is a chiral center. So we're going to need to draw the bonds there with the correct stereochemistry, so either with the right solid wedges or the right dashed wedges, to make sure that the chiral center there is S. Okay, so I'm going to erase these colors. Now, I don't know how to draw this yet, but here are the 2 possibilities. Either the OH could be coming out at us, and the methyl group could be going away, or the OH could be going away, and the methyl group could be coming out at us. So let's think about each of those, see which one gives us the S configuration. Okay, so the first step in the CIP rules, and I'm going to do this a little faster since we've done this in more depth in previous videos, and since there are many videos from Organic Chemistry 1 that you can use to practice a little bit. But the oxygen has the highest atomic number, and so it gets a priority of 1. The rest are carbons, so you'd want to make a table. We'll make a table for the carbon going down, the carbon going right, and the carbon going left. Going down, that carbon is bonded to 3 hydrogens. To the right, this carbon is bonded to a carbon and 2 hydrogens. To the left, this carbon is bonded to 2 carbons and a hydrogen. And when we compare those, the top 2 tie. The one going down has the lowest priority, and so that will be 4. Going to the next row, you can see this one wins, the isopropyl group, and so that will have a priority of 2, and this other one will have a priority of 3. Okay. So those are our priorities. Now, I can fill that in on the other one below. These are all the same groups, so they should have the same priorities. The only difference is their orientation in space between the structure on the top and the structure on the bottom. Okay, now again, we want the structure that's S. Which one of these is S? Let's start with the one on top. Now that we've assigned the priorities, the second step is to make sure that 4 is going away, and here it is. So we can go ignore 4 and go from 1 to 2 to 3, and that goes clockwise. If it's clockwise, then it's R. It's the right-handed version of itself, so it wouldn't fit into left-handed pockets. And you could remember that because going from the top to the bottom of an R, you go clockwise. On the other hand, in the one at the bottom, 4 is not going away, it's coming out at us. So if you go from 1 to 2 to 3 here, it looks like you would have R, but because 4 is coming out at us, you cross that out and you put the opposite, it's S. So the one on the bottom is S. And because S is what they want us to draw, the one on the bottom is the correct structure. So that one on the top is not, the one on the bottom is the correct structure. It's S. And so that would be what you would want to draw for S,2,3-dimethyl 3-pentanol. So I think the chiral center there is probably the trickiest part, but it gives you some good practice with becoming more fluent with those chiral centers.